Hello. In this video, I'm gonna be introducing a game known as Race to 15. Okay, so I'm gonna explain the mechanics of the game. So it takes two players, and each of these players must know how to add. That's like the minimum requirement. So even like kids, kindergarten who can like add one up to 9. Okay, one-digit number is good with this game. Okay, so the goal of the game is you need to pick out numbers from 1 to 9. So as I wrote the digits right here, you pick out numbers from 1 to 9. The first guy, okay, who can pick 3 digits that adds up to 15, and exactly 15 is the winner. Hence the name Race to 15, okay? And so the idea is, for example, let's say blue and green will battle, and let's say it's blue's turn first. Let's say blue will pick 9, okay, and so green will pick, let's say, I don't know, green will pick like 1, okay. So now if next turn it's blue's turn, if he will pick like 6, he will say, I won. 9 plus 6 is 15. 9 plus 6. That's not how the game works. So you should have 3 digits that adds up to 9, okay. Sorry, adds up to 15. If it's only 2, that doesn't count, and the game moves on, okay. So for example, what green can do here is he can pick, for example, the number, I don't know, 8, for example, and then the game goes on. So, for example, had the game been, let me show you a winning game. So, example, blue picks first. He picks up 9, and let's say green picks up 2, and then blue again. Blue will pick up 1. So, note that blue already has 9 and 1. So 9 plus 1, he only has 5 left to win. Let's say green will pick, I don't know, 7. Okay, so the plan of green is that, I have 2 and then I have 7. So 2 plus 7 is 9. Next turn, if I pick up 6, I win. Okay, but of course, he forgot that blue already has 1 and 9. And so if blue will pick up 5, blue is the winner, okay? So that's how the game goes. So you need 3 digits. It has to sum up to 15. Whoever does that first with 3 numbers whose exact sum is 15, the game ends, and the one who got 15 is the winner. And in fact, the nice thing about this game is you can do it mentally, you know? So you just need to remember what your opponent picked up. So that's like one of the challenge. But if that's what you want to learn, if you watch this video just for that, the mechanics of this game, it ends here, okay? So you can now stop watching the video, go out and conquer and spread this game to the people you know. You're like, hey, I know this 2-player game, which is very cool. You only need to know how to add, okay? So you can stop watching now. The rest of this video will be teaching you how to get good, okay? How to get good in Race to 15, okay? So Git Good is like a video game term for like get better, okay? So here I'll give you a technique that is very, very amazing, okay? But in order to do that, let me take you back to memory lane, to something that would initially like it would sort of like look like a little bit related, but later you'll see the connection, okay? Back in grade 5, we have this like substitute teacher, okay? And back in grade 5, you know, when I was in elementary, I was really like very noisy, and you know, so I think the substitute teacher, I forgot her name. Her name is escaping my memory right now, but I think she got irritated with me. She said, hey, Marvin, come here. I'll give you a problem to solve. You're very noisy. So you solve this until you can solve this. You shut up. Okay. I'm like, yeah, I was so confident with my mathematical prowess when I was in elementary. You know, I was like the contestant of like math Olympiads and so on. So I'm like, bring it on. So she said, okay, draw a 3x3 square like chess, but only 3x3. And so I did that. I'm like, okay. Very, very straightforward, this substitute teacher. What is she trying to do? Okay, there's your 3x3. And so now she said, okay, the numbers 1 to 9. Okay, so you can see, I think this is related to Race to 15. So she said, arrange numbers 1 to 9 in such a way that all the rows, okay, all the columns, and the 2 diagonals, if I take the 3 numbers in them and add them, all will be summed up to 15. It looks like Race to the 15, but anyway, so I'm like, that's interesting. So I'm like, if I write 1 here, for sure, 2 can't be here because 1 plus 2 is 3. I need 12, but I only have 1-digit numbers. This is very awesome. Okay, so I was so intrigued by that, man. And in fact, I was like, during that day, I wasn't able to solve it. I was like, Mom, I'm sorry, I wasn't able to solve it. I'm stupid. Can I like bring it home? And then I promise you, like, the next day, I'll show you the solution. And she's like, okay, bring it to your home and then work on it. And so I brought it home. I really spent my time, doing trial and error, trying to arrange 1 to 9 so that all the rows, all the columns, and the 2 diagonals will give 15. Okay, I found it. Okay, so the next day I'm like, Mom, here you go. I found the answer, and in fact, I'm gonna write it here, the solution. Okay, so this solution is actually not unique. Okay, in other words, it is you can find other combinations, but it's trivial because one way you can find another solution is you can rotate this like along the diagonal or along the center column or row to get another combinations. But basically, those are like trivial rotations and so on. But you get this combination, and in fact, if you check, for example, this first column right here, 4 plus 3 is 7 plus 8. Aha, that's 15. 9 plus 5 plus 1. Aha, that's 15. 2 plus 7 is 9 plus 6. Aha, that's 15. How about the rows? 4 plus 9 is 13 plus 2. Ah, that's 15. 3 plus 5 is 8 plus 7. Ah, that's 15. 8 plus 1 is 9 plus 6. That's also 15. Okay. How about the diagonals now? I'm like, the diagonals should be 15. 4 plus 5, 9 plus 6. Ah, that's also 15. How about on the other diagonal? 2 plus 5, 7 plus 8. Aha, that's also 15. Pa, pa, pa. Okay, done. I got it. I'm like, this is awesome, man. I didn't actually know that this thing, this entity right here, it is called something else in mathematics. It has a name, okay? And I was able to learn that when I was in grade 6. So in grade 6, I was a contestant also of Philippine history, okay? And I already won the regional competition, so I was to represent Region 7 on the national history competition. And it was like the first time I was gonna ride an airplane, so my coach was like, okay, you need to stay at our place with her husband, who is a historian, Dr. Sitoy. She said, you stay at our place so that we can go to the airport early in the morning. Okay, so I did there. I went to their house, and then we did a little bit of review, and like around, I don't know, 8 p.m., 9 p.m., she's like, okay, go to your room now. You'll be staying here. I want you to sleep right away because, we'll be early tomorrow. And of course, the thing is, when I went into the room, every room in the house of Dr. Sisto is surrounded by this like huge bookshelf. And I was like, oh man, I don't think I can sleep early because like I love books and I look around several books. I found this book, okay? And this specific book that I found discusses this specific problem, okay, that my substitute teacher gave me when I was in grade 5, okay? And in fact, during that night, I learned that this beast right here is known as a magic square, okay? And so I read during that night, and the nice thing, the ironic thing is that I learned the algorithm of how to write the answer of this magic square, okay? So during that time, I was studying for Philippine history. I already forgot a lot of the trivia about Philippine history, but the ironic thing is this guy right here, the algorithm to produce the magic square so that it gives all the rows, columns, and diagonals equal sum, I still remember, okay? And I'm gonna show it to you now. And so I read, okay, in that book that, for example, let's go back to this 3 by 3 square. And to make it a little bit nicer, let me insert a table right here. Okay, so we're gonna need a 3 by 3, so one more row and one more column. Okay, so we have this 3 by 3 table. So in that book, I found the algorithm, and the algorithm says that first, okay, number 1, what you need to do is write the number 1, the beginning of the count, at the center of the lowest row. Okay, so what does that mean? In our case here, I write 1 there. Okay, simple. Okay, the next algorithm, from where you write 1, move down and move right with wrapping. Okay, what does that mean with wrapping? It means, so I'm at 1 now. If I move down, there's nothing to move down to. So when you say with wrapping, then you end up on top. Okay. Now, if you are on the right, already on the rightmost, there's nowhere to move right. So with wrapping, it means you end up on the left. So for example, 1. So I move down, I end up on top, and then I move right. So I write 2 here. Okay? So now I move down, I end up here, and then right. So you have 3 right there. Okay? You move down, and then I move right. Ah! It's occupied. There's 1 there. And so we get to the third and last algorithm. If occupied, okay, go back to the number and go up. Okay, so what does that mean? So I was at 3, right? I went down and then I went right, but the right is occupied. There's 1 there. So what algorithm 3 says is I go back to that number, which in this case is 3, and then instead of going down right, I go up instead. So there I write 4. And then I go back to the previous algorithm. So at 4, I go down and right. So I end up here. Down and right, I end up here. So at 6, down, you end up at 2, right. Ah, it's occupied. There's 4. So you go back to 6, and then you go up. 7, okay? And then you go down, you end up at 6, right? So you end up at the blank space here, 8. You go down, you end up at 4, and then right. So 9 is there. So in fact, it's exactly the same as the solution I wrote here. But of course, now we know the algorithm, okay? And it adds up. And the nice thing is you can like tackle bigger, what do you call this? Bigger squares. So for example, if I'm gonna, let me insert here another table, okay, if I can. So let me insert, oh shucks. Let me insert a table. So this time 2, 3, 4, 5 rows, and then columns 2, 3, 4, 5 columns. Okay. So let's look at this table right here, and then let's do our algorithm if it works. Okay. So write 1 at the center of the lowest row. So we start here. 1. Okay. Go down and then right. So down, so you end up on top, and then right. So 2. Okay. And then down and right, you have 3. Okay. Down and right, so you end up here. 4. Down and right, 5. Down and right. Aha! It's occupied. Okay. Because there's 1 there. So you go back to 5 and then go up. 6. Down right. 7. Down right. 8. Down, so you end up at 2, right? So 9. Down, you end up at 3, right? So 10, okay? And then down, right? Ah, it's occupied. So you go back to 10 and then go up. 11. Down, right? 12. Down, right? 13. Down, right? 14. Down, right? 15, okay? Down, you end up at 9, right? 11, ah, it's occupied. So go back to 15 and then go up. So you have 16. Down, you end up at 15, right? So it's blank, so 17. Down, you end up at 11, right? So it's blank again, 18. Down, right, 19. Down, right, 20. Down, you end up at 14. Right, you end up at 16. Aha, it's occupied. So go back to 20. Go up, 21. Down, right, 22. Down, you end up at 16. Right, it's blank. So 23. Down, right, so 24. Down, you end up at 18. Right, 25. Okay? So now let's check if all columns and rows have the same sum. Of course, I'm not going to check it all because there's now a lot here. Okay, but let's look at this first column, for example. 23 plus 17, aha, that is 40. Plus 4, that's 44. Plus 10, that's 54. Plus 11, 65. Aha, so now, how about this row? So if it's not 65, then it's wrong. Okay, but we expect it to be 65. 11 plus 18, that's 29. Plus 25, that is 54. Plus 2, that's 56. Plus 9, indeed, that is 65. And if you really want, you can like check all the other of the columns and the rest of the rows. You will find out that it is indeed all equal to 65. Okay? So now you see that there's something, there's a number, there's a sum associated with a specific square. So for example, for 3 by 3, we have this number 15, the sum of all its rows and all its columns and its 2 diagonals. We call that thing, the 15, we call it the magic constant, okay? Associated with a square of side, let's say S, okay? So let's call it M sub S, the magic constant associated with a magic square with side S. So for example, when S is equal to 3, so you have M sub 3. This is 15, okay? When M is equal to 5 for our 5 by 5 case. This is equal to 65. Okay? And then you ask, oh, how about like 4 by 4? So in fact, 2 by 2, you can't do a magic square. You can't try it. It will never do the diagonal, all the rows and columns. It will never sum up to an equal number. So it starts with 3 by 3. There's a 4 by 4, but I want you to explore that if you want. So like, how about even-sided magic squares? You can do that. I'm gonna do odd numbers here. But in fact, there is a general equation to get the magic constant associated with any magic square, even if it's very big, even if it's like 1 million sided, okay, to ask what is the magic constant associated with that square, okay? And to do that, we're gonna need a very basic arithmetic result, which says that the sum of all the numbers up to some integer n is equal to 1/2 n plus 1. Okay, so this is a known result in mathematics. So for example, when n is equal to 3, what does that mean? I want to sum all the numbers from 1 up to 3. Okay, obviously this is equal to 6. Does our formula on the right hand side works? It does, because that is just 1/2 times 3 times 3 plus 1, which is 4. This is equal to 12 over 2. It's also 6. Okay, so you might ask, does this equation work for any n? Well, we can prove that. Okay, and to prove relations like this, we use proof by induction. So I think I can leave. No, let's just prove it. Okay, it's straightforward. So we'll prove this by induction, mathematical induction. And basically, the idea of mathematical induction is that you have an expression, you want to show that that expression holds for all positive numbers, okay? And so in order to do that, this is what induction does. Induction does what it does first is it has what is called the base case, okay? The base case meaning it has to start. Your equation has to start somewhere. So think of proof by induction. Think of like lining up dominoes all the way up to infinity, okay? So you want to know if a certain expression works from 1 all the way up to infinity. So think of it like pushing the 1 domino. So if it works, what it means, if I push 1, all will like cascade all the way down to infinity. That's what it means when an expression works from 1 all the way down to infinity. So in order for it to work in the first place, you have to push the first domino, okay? Otherwise, it doesn't start, it doesn't work, okay? So there has to be a base case. In other words, this has to work for the starting case, which in this case is 1. So for the base case n equals 1, the left-hand side is trivially 1. You're adding 1. The total is obviously 1, but let's see if the right-hand side works. So you have 1/2 n. N is 1. N plus 1 is just 2. So this is, of course, equal to 1. So in other words, yes, we have a base case. We were able to push the first domino, okay? So now if you're doing a cascade of dominoes, what's the next thing that you have to make sure? You have to make sure that there's no gap somewhere, because if I push the domino, it cascaded. Suppose like at 99, the 99th domino, the space between the 99th domino and the 100th domino is very huge. So when the 99 toppled down, it didn't hit the 100. So in other words, my expression doesn't work for 100 and above, okay? So in other words, instead of picking 99, let's pick a random number k, okay? So now we need to show if this expression holds for that random number k. So let's write this down. So for k, for a random number k, so 1 plus 2 plus 3, all the way up to k. Let's see if this, we assume that this expression reaches k, reaches that number. So in my previous example, the 99th, if it reaches that number, then it has to push the next number. So in other words, we should be able to extract the k plus 1 case, assuming that it holds for k, okay? And if you can do that, then you're done. You have proven the expression by induction. So you've proven the base case, and then you've proven the inductive process, okay, that it goes on forever, okay? So we assume that it holds for k, we prove it for k plus 1. How do you do that? Well, for k plus 1, you're adding 1, 2, 3, all the way up to k plus 1. So what you do is you just add, in this case, k plus 1 on both sides, okay? So I add k plus 1 on both sides, okay? And so what happens is I can rewrite the right-hand side as, let me see. So let me factor 1/2. So let me write this as 2 over 2 k plus 1, okay? I did this so that I can factor 1/2 k plus 1 k plus 2, okay? And this is exactly, okay, this is exactly what we want. This is exactly the expression for k plus 1. So in other words, if k holds, k plus 1 holds. We're done, okay? That's basically proof by induction, okay? So that's a segue right there, but yeah, it's important to know that this thing holds. Why do we even want that? Why are we even interested with the expression right here? Because what I'm gonna do now is I'm gonna sum all the entries in the magic square. So in other words, for the 3x3 magic square, I want to add 1 plus 2 plus 3 all the way up to 9, okay? Let's call that T sub S, okay? So in other words, I want to add, this is the sum of all the entries of an S-sided magic square. So explicitly, this is 1 plus 2 plus 3 all the way up to S? No, because S is just the side. The number of entries inside an S-sided magic square is, of course, S squared, okay? And from our equation above, the total, you just substitute S squared for N. The total will be 1/2 S squared plus 1, okay? That's the sum of the entries in the magic square. Why is that important? It is important because we will now need that for our magic constant. How does that give us the magic constant? Let's look at this 3x3 magic square right here, okay? This 3x3 magic square. The sum for this guy, TS is equal to, so S is 3, so that is 3 squared is 9. 9 over 2, S squared is 9 plus 1 is 10. Okay, so this is equal to 45. Okay, the sum of all entries for the 3x3 case is 45. But what is a magic constant? Magic constant is just the sum of a single row or of a single column. How many rows are there in a 3x3 magic square? There are 3. How many columns are there in a 3x3 magic square? There are 3. Okay, so in that case, in order to get the magic constant for this case, I just divide the total of all the entries divided by the number of rows. So in this case, 3. That gives you 15. Okay, so in general, you take, to get the magic constant, you take the total of all the entries and then you divide it by the number of the sides, because obviously that gives you the number of rows or the number of columns. Okay, so if you simplify this, this gives you 1/2 S squared plus 1 divided by S. Of course, that's just 1/2 S squared plus 1. Okay, let's check. We've already checked it for S equals 3, but let's just use this formula to see if it's correct. 1/2 3 multiplied by 3, so 9 plus 1 is 10. So you have 10 over 2 is 5 times 3. Indeed, that's 15. We already know that. How about MS equals 5? Okay, for S equals 5, you have 1/2 5 multiplied by 5 squared is 25 plus 1 is 26. 26 divided by 2 is 13 times 5 is, of course, 65. Okay, so we've established that this equation right here gives us the magic constant, that is the sum of every rows or every columns of a given S-sided magic square. And in fact, this holds for even if S is even, okay, as long as S is greater than or equal to 3, because magic squares starts at S equals 3. Okay, so now you might ask, okay, so what does this have to do with the raise to 15 game? Because I told you it will help you get good with the game. Okay, so the thing is, the technique actually is, let me redraw again here let me insert again here the table, okay, for the 3x3. Okay, so let's make that 3x3. So let's write again the solution. So you have 8, sorry, let's draw 8, 1, so 1, 6, 3, 5, 7, okay, 4, 9, 2. So the nice thing is, it's to get good at raised to 15 game. It's nice if you memorize this, okay, this magic square. Let me tell you why. Let's play the game. Again, what's the rule? The first guy who obtains 3 digits between 1 to 9, alternating. If one gets, let's say, number 5, the other one can't get 5 anymore. The first one who gets 3 digits that adds up to exactly 15 is the winner. Blue goes first. Let's say blue picks out 5. Okay? And then green will be like, okay, you pick out 5, whatever. I'm gonna pick out 4. Okay? And blue is like, aha, I have 5. Right now I'm gonna pick up, let's say 8. Okay? Because his plan is 8 plus 5 is 13. In my next move, I'm gonna pick up 2. But green is like, I know what you're doing. You're gonna pick up 2, so I'm gonna pick it up for myself, so you won't pick it up. And then the blue is like, oh my god, he has 4 plus 2. If he picks out 9, he wins. So I have to pick out 9 myself. Okay? And then green will be like, I think blue is scheming me. Blue already has 8, 9, and 5. If you combine 9 and 5, you have 14. If he picks 1, he's the winner, and 1 is not yet picked. So I'm gonna pick that myself. Okay? I'm gonna pick that myself, and the game continues. If you've noticed by now, what is this? What are we doing? Forget the numbers. Okay? Forget the numbers. What is blue and green doing here? What they're doing is they're playing tic-tac-toe, right? Blue is like, okay, that's my move. Green will be like, okay, this is my move. Blue will be like, that's my move. And then green is like, I'm gonna cancel that move. And then blue will be like, I want to go here. Green will be like, I'm gonna cancel that move. So it's like playing tic-tac-toe, okay? So, but the nice thing is, it's mental tic-tac-toe, man, okay? So in fact, the race to 15 game, okay, without doing anything, like you're just like looking at each other in the eye, picking 3 numbers that will sum first to 15, you can think of it as a mental tic-tac-toe. So like you come to someone and you'll be like, hey, how are you? Do you want to play tic-tac-toe? It's like, okay, let's write. Do you have a paper? No, we're gonna do it mentally. It's like, whoa, what? How can you do that mentally? And then you get to explain this, the idea of magic squares. And in order to get good, it's nice to be familiar with the layout of 1 to 9 in the 3 by 3 magic square. Because if the other guy doesn't do that, if he thinks of race to 15 game as something like, okay, picking up digits from 1 to 9 and then just adding them, if you think of the 3 by 3 magic square and then think of it like playing tic-tac-toe, man, you have a very huge advantage over your opponent. Okay, so this is what I want to show. And in fact, if your opponent is already like very good with that, you can extend the game. You can, instead of like race to 15, you can make it race to 65. 65 being the magic constant of a 5 by 5 magic square. So you say, so the rule now is, okay, let's pick numbers 1 to 25 alternating. The first one who can get 5 digits, whose sum is exactly 65, is the winner. Then you have another game, race to 65, okay? But of course, I would, if I like play this with like elementary kids and so on, I would of course start with the race to 15 rules, okay? And keep in mind, if you're like the more mature person who thinks he or she is the most mature person mathematically, then you should know that this is nothing but a tic-tac-toe on a 3 by 3 magic square. Okay, so that's all I have for you in this video. And again, I made this all things possible with my iPad, and I'm also trying to take a video of myself, and let's see how it turns out. Okay, and if you've watched with me, this is like almost 30 minutes, but if you learned something or if you enjoyed watching, thank you very much. I hope you learned a lot, and I'll see you next time. Bye-bye.